Raw data is a mess. When systems ingest millions of real-world records, the information is unstructured, making it a computational nightmare to process. Today's networks generate enormous, continuous streams of information. These massive data lakes are technically rich, but in their raw, unsorted state, they're effectively useless for analysis. To extract actual meaning from that noise, we have to impose strict programmatic order. We must structure the information before we can ask it meaningful questions. This applies across every analytical field. Statistical analysis requires sequenced inputs. Finance prioritizes transactions by exact amounts. Healthcare sequences metrics to spot trends. This chart outlines the basic transformation we need. Before any advanced analytical operations can run, we have to perform a sort, rearranging random data points into predictable, searchable sequences. Sorting algorithms are the mathematical engines that do this work. They take chaotic inputs and force them into ascending or descending alignment. For this lesson, our practical objective is specific. We are going to write a program that calculates the exact statistical median from a raw dataset. The median is simply the value that sits directly in the center of a group of numbers, dividing the dataset into two equal halves. You cannot logically find that midpoint if the dataset hasn't been ordered first. If the numbers are random, the physical center means absolutely nothing. Reaching that center value requires building a specific engineering stack. We have to master memory allocation to store the data, iterative traversal to read it, and algorithmic manipulation to order it. To organize data, you first have to put it somewhere. Programmatic order starts at the absolute bedrock level, allocating physical memory storage. Look at this graphic detailing single-dimensional arrays. This is the foundational structure that gives data a linear home, storing a sequence of elements in a single row. A 1D array, or list, holds a sequence of variables of the exact same type, placing them back-to-back in memory. Notice the numbering below the array boxes. In computer science, we use zero indexing. Because of zero indexing, the first piece of data in an array lives at index 0, the second at index 1, and so on. The address is an offset from the very start of the list. Simple lists work well for a single row of temperatures or test scores, but they fall short when you need to store relational, grid-based information. Here we have multidimensional arrays. As the 3x3 grids in these code blocks show, we can nest arrays inside of other arrays. This creates a 2D matrix. By adding an additional dimension, we organize the data into distinct rows and columns, mapped by two separate index numbers. This structure is how programmers plot spatial coordinates, manage tables of database records, or define the specific pixel values in a digital image. Arrays give our data rigid, predictable physical addresses, but those values are trapped in static memory until we introduce a mechanism to go visit them. To read or manipulate the contents of an array, we have to systematically traverse its coordinates. This diagram shows exactly how we do that, using a standard for loop. Look at the code blocks for C++, Java, and Python. Loops automate repetition. You define a start, a condition to check, and a step forward. The loop uses a variable I as a counter. Notice how this counter perfectly aligns with the array's zero-indexed coordinates. On each pass, the loop runs its logic and then automatically increments I by 1, ensuring every single index is sequentially visited without manual coding. Traversing a 1D list is straightforward, but moving through a two-dimensional matrix introduces a routing problem. You have to handle both rows and columns. The solution is a nested loop. The outer loop controls vertical progress, locking onto a specific row. While it holds, the inner loop executes completely, traversing horizontally through every column. Only when the row is finished does the outer loop tick forward. Loops get us complete read access to inspect every coordinate. But to actually sort the data, reading isn't enough. We need write access to change sequences dynamically. Sorting an array strictly requires a single repetitive action, evaluating two elements and swapping their physical positions. But if you try to swap two variables directly in standard programming logic, you run into a data collision. If you assign variable A's value directly into variable B, the computer completely overwrites and destroys B's original data. To prevent data loss, we declare a third empty variable as a temporary holding space for a safe three-step swap. Copy A into temp. Next, move B into A. Finally, pull that original A value from temp and drop it into B. When you take this three-step swapping logic and place it inside a nested loop traversal, you have built a sorting algorithm. One of the most foundational algorithms in computer science is the bubble sort. The core mechanic is entirely mechanical. Loops compare adjacent elements side by side. If the left item is larger than the right item, they execute a swap. To measure how efficiently an algorithm like this performs, we use algorithmic time complexity, mapped out via big O notation. Bubble sort operates at O of n squared time complexity. Because it relies on nested loops checking the entire array for every single element, the number of operations multiplies exponentially. On massive datasets, it becomes incredibly slow. Despite the high computational cost of nested loops, this specific stack of tools, memory allocation, looping, and swapping, successfully transforms a chaotic array into a perfectly ordered sequence, giving us the baseline we need for analysis. Now that our array is fully ordered, we can execute the primary analytical goal we established at the start, calculating the precise statistical median. Looking at this breakdown, the median is the true center value that perfectly divides our sorted dataset into two equal halves. The mathematical approach to finding that physical center changes entirely depending on the total length of the dataset. This is why the modulus operator is so important. As shown in the bottom section here, modulus allows the program to check a dataset's parity, determining immediately whether the total length is an odd or even number. When you calculate the length modulus 2 and the remainder equals 1, the program knows it is dealing with an odd number of data points. Look at the left side of this graphic. For an odd dataset, the logic path is incredibly direct. The algorithm simply targets the exact middle index, extracting the 5. But if the length modulus 2 leaves a remainder of exactly 0, the algorithm branches to handle an even number of data points. As you can see on the right side, an even dataset has no single center. The middle falls exactly between two indices, so the algorithm isolates both the 7 and the 9. Those two central values are then added together and divided by 2. The result is the true mathematical average median of the dataset. Extracting high-level insights from raw data is never magic. It is the strict linear application of a dependency stack, allocating memory in arrays, traversing with loops, sorting via logical exchanges, and finally querying that ordered data with absolute mathematical precision.